Wonderful. Welcome, everybody. We're happy to have you here today for this Design Safe webinar. This is our first Dataset Award webinar for the 2023 year. And Charlie Day is usually here to do the introductions, but he's traveling today, so you're stuck with me, Scott Brandenburg, at UCLA. I'm one of the co-PIs for the Design Safe project. So before I turn it over to Dan Cox, I'll just remind you that we have a survey. I'm showing a QR code now. I'll show this again at the end of the webinar. So we do really appreciate your feedback, and we adjust some things in the webinar based on feedback that we receive. So please take a minute at the end to provide that feedback to us. And I'll move forward and just introduce Dan. And as we go through the webinar, if you have questions, feel free to use the Q&A feature. Notice that there's a Q&A feature and then there's a chat feature, and the icons look almost the same. Please use the Q&A feature to ask your questions, and then when we get to the end, I'll facilitate those questions, and Dan will provide answers as we go. All right, so Dan Cox is a professor at Oregon State University. His research focuses on community resilience to coastal hazards, including tsunamis and hurricanes, and its effects on the built environment. He's also the PI for the NARI Experimental Facility for Hurricane Surge Waves and Tsunamis at Oregon State, and a co-organizer for the NARI Summit in 2022 and 24. And he's done a lot of other things, and I won't use up his time reading through that list. So before I hand it over, Dan, I just want to congratulate you on the Dataset Award. I think that it's wonderful to have, these well-curated and very clear data sets in Design Safe for other people to use. And so congratulations on that. And I'll go ahead and stop my share and turn it over to you to talk about Seaside Testbed Data Inventory for Infrastructure, Population, and Earthquake-Tsunami Hazard.
Right. Thank you, Scott, and Natalie, too, for organizing the webinar. And thank you for this tremendous honor. It was great to get the award on behalf of the team. We thank everybody at Design Safe. I will make the slides available. Obviously, this is recorded, but if people want the slides after the presentation, feel free to contact me. I will share the slides now in presenter mode. Everybody can see the screen okay?
Yep, looks good.
Awesome. All right. Yeah, so this is the Seaside Testbed that we developed for community resilience modeling. The specific title on Design Safe is there, PRJ 3390. And as Scott mentioned, I'm Dan Cox, professor in civil and construction engineering here at Oregon State University. So partly why this testbed? What was it about? Why did we start with the Cascadia Subduction Zone hazard? So this is a big issue for us here in the Pacific Northwest, as well as around the world, where they're facing threats of multiple hazards from earthquakes and tsunamis. In our area in particular, this last event happened 323 years ago, 1700. It happens roughly every 300 to 500 years. We see a really large subduction zone earthquake, and scientists estimate there's about a 14% chance of having this in the next 50 years. What's significant from, let's say, engineering and social science perspectives is that it's only since about the 1980s that scientists have agreed that there's a threat from the Cascadia Subduction Zone. So a lot of our infrastructure and plans for building these resilient communities are out of date. We really have to think very carefully about how we're going to make our coastal communities resilient for this type of event. Why Seaside in particular? Partly we were interested in this multi-hazard event with strong ground motion and tsunamis. It's a relatively small area. The population when we started from the 2010 census was 6,457 people. So we thought it would be easy to build out an entire city at the parcel scale. And it's sort of it's got a little bit of this, a little bit of that, but, it was easy to identify where the schools, the critical facilities were. So we felt it was kind of the right size to build out a test piece, if you will, for testing some resilience models. And I think Seaside in particular has a very urgent need for solutions to increase their community resilience. So that's why we went with Seaside. And then for those of you who aren't extremely familiar with tsunamis, here's what one looks like. This is a photograph taken by Kyoto News Service in Japan, March 11, 2011, with the Sendai. This is looking south along the Sendai Plain. The flow depth on the shoreline, or at the water's edge here, is about 8 meters. And that's about what we're expecting in Seaside with a magnitude 9 event. So this gives you some idea of the scale of the problem that we're looking at. And obviously you can see a lot of infrastructure, that's being impacted, buildings. There's an airport here to the right, transportation. So there's a lot of the built environment as well as the natural environment. You can see the trees as well. And then of course, the people. So with that, when we built out our test bed, we were very focused on incorporating these 3 aspects. We wanted to have the natural hazards, so the natural system, we wanted to have the built environment, and then we wanted to have the human system. So disasters are a convergence of these 3 systems. So we felt like, okay, well, let's get a little bit of each to start with, and then kind of go around, try to build up these as best we can. So I'm going to talk about these in 3 parts: natural, built, and human systems, starting with the natural systems first. This was a lot of work done by Hyung-Soo Park, a PhD student and later postdoc here working with me, where we went all the way to the beginning to define using inversion models from elsewhere, defining the slip distribution along the Cascadia Subduction Zone, and then using this parameterized model to generate dozens and dozens of numerical simulations using nested grid. We used NOAA's model to initiate the tsunami. And then we used CoolWave, which was developed by Pat Lynette at USC for the inundation of Seaside. So Seaside's shown down here. So the details of this modeling aren't available in the test bed. What we did instead was to use a logic tree model to combine all of these different scenarios, and then or simulations, I should say, and then expert opinion or estimates on what we think are the likelihoods of these different magnitude events going from 8.8 up to 9.2. Best estimates of the distributions of the slip and location of the peak slip and so on. And we constructed annual exceedance probability curves or maps for the city of Seaside. So we kind of followed, you could say, what had been done before in earthquake engineering, but this was one of the first times where we could actually build out different maps, inundation maps with associated annual exceedance probabilities. So that was a really big step. Rather than just having scenarios for risk-based modeling, we wanted to have a whole suite of annual exceedance probabilities. So here we're just showing 3 in the test bed. We put 7 ranging from 100-year all the way up to 10,000 year. So this one, this hazard is just showing the maximum flow depth. But we also have included maximum velocity, maximum momentum flux. So these are all quantities that can be used, for example, to estimate the likely damage on infrastructure such as buildings, bridges, and so on. We also included things like duration time of flooding. So how long will the area be flooded? This is relevant, for example, for first responders and people who have to go in for search and rescue. So we included that. I think this is one of the first instances of having duration maps. And then consistent with all of the tsunami inundation work, we also spent some time using existing ground motion prediction equations to build out consistent ground motions. So including peak ground acceleration and all the different intensity measures that one would use for estimating structural damage. So this is, again, a lot of work done by 2 people here, Hyung-Soo Park and Shafiq Alam now, who are both either in or headed to University of Hawaii. Got a few of the papers listed at the bottom of the talk, and then at the end of the talk, I've got a whole bunch of papers that utilize this testbed. So that's the first 2 anyway, earthquakes and tsunamis. There's lots of other natural hazards, these cascading consequences, for example, landslide, liquefaction, debris, potential for fire outbreak, and so on. These haven't been included in the test bed, but we're very interested in people who would be adding this to this type of test bed. I think that's what's exciting about having it up on Design Safe. There are ways to link to other data sets that might have more hazard information. Moving on to the built environment, you can see the big five are listed here: buildings, transportation, energy, water, and communication. And then in each of those, you can just keep further dividing it. For example, buildings can be subdivided into critical facilities, residential, commercial, and so on. So just like we did with the natural hazards, we try to pick these apart and figure out which ones can we get into this test bed. Starting with the buildings, you can see an aerial photograph here of the city with the shoreline up on the front. And, it's not hard to imagine that this is where you get the highest concentration of steel reinforced concrete buildings, also some unreinforced concrete. This is the central core of the city, the business district here. See lots of roads and bridges crossing the Nicanicum River. And then to the left and right here, this is mostly residential structures. So it's mostly going to be wooden houses. And we went through a system of using tax lot information, a lot of Google Street View from here with the grad students. And then we took a team up to Seaside to do some rapid visual screening and kind of do a check on what we were seeing from the tax data. Since then, there's the National Structures Inventory, which we've also used. It's not in the test bed, but it is interesting to compare these types of methods with NSI and other types of data sets. But with the tax information, we're able to get things like the material of construction, whether it's wood or concrete, number of floors, the likely seismic code that it was built to, and all these different attributes that you use for using typical fragility analysis. We went another step further, trying to get at least the freshwater network. So that's in the test bed. This is just showing you the water system. We've got the location of the water pumps, the different diameters of the pipes, and so on. A lot of people have done connectivity analyses, but you can also do like a full flow model if you're using EPA net or something similar. So we have the water system that was based on from the city manager, this public utility. So that was public information readily available. The electric power net was a lot more difficult to do. So this was done by John Vanderlint and his students at Colorado State, where they built a synthetic electric power network. But, listening to other experts, definitely not myself, they said this looks like a realistic electric power network with one substation. And then, the water pumps that would use the power, for example, are readily identified in that data layer. And then, because it's public information, it was very easy to get the road network. Working with the Oregon Department of Transportation, we have a lot of information about the bridges and so on. So there's a pretty good transportation network as well. You can see on this figure, for example, critical facilities like fire station and hospital are well identified as well. So that gives us some outlook on what the built environment looks like. Definitely it could be improved, especially, for example, looking at fuel, communication, non-networked power like generators and solar power, communication, I think I mentioned that, wastewater, stormwater. So there's other aspects of the built environment that could be added. Welcome discussions around that, but at least we've got, I think, enough if people want to look at, for example, interdependencies between water, electric power, and transportation, for example. Moving to the last subsystem, this is the human system and the one that I know the least about. But some of the main issues, for example, looking at life safety, the vulnerable populations, direct economic losses, business continuity, and things like food security were all deemed important to try to include. A lot of this work was done with Nathaniel Rosenheim. He's a research professor at Texas A&M University with an expertise in this area. So he helped us develop a population map that is realistic for the city of Seaside. So as many people know, it's very difficult to get parcel scale information without revealing personal information and things like that. So his work is really good at using the general statistics that are available from the census data and then downscaling that to the parcels, including owner occupied and rental units and all that kind of stuff. So it's very detailed information. It's not a digital twin per se, but it's very realistic distribution of people, including attributes like ethnicity and race and other factors, income. We also had an interesting aspect of Seaside. You can imagine it's a beach tourist community. Just talking to some of the locals there, they said that some of the big issues are the change in population from day to night and from weekday to weekend. They said in the summertime, the population can triple on a sunny weekend. So we also created data layers that look at the transient population. So not based on census data, but based on the commercial structures, the hotels and things like that, as well as the attractions, which obviously for the beach, you can see the hotspot there, everybody down at the beach in the daytime. So this was developed more for population evacuation modeling, which I'll talk about very briefly at the end. And then also in the social layer, we added a CGE model. So this is Computable General Equilibrium Model. This was work led by Harvey Cutler at Colorado State University with his graduate student and now postdoc, Hui Young. And this is a model that allows the flow of labor and capital between households, firms, the rest of the world, and so on. And as the earthquake and tsunami happen, that shocks the system, so the system's out of equilibrium. And then this model allows estimates of the return, the indirect losses, number one, that's probably the most use of it, and then can be used by other people to look at rates of recovery and things like that. So this just gives you a snapshot of how the different economic sectors, are parsed out in this CGE model between housing, service, retail, and so on. Gives you a rough idea of the number of buildings affected, for example, with healthcare, for retail, and so on. So that's it on the kind of the overall development of the test bed. Again, there's always more that can be added, especially here in the cases of business continuity, things like food security, health, education, and so on. As I mentioned it, or might not have mentioned, but this work was initially put together through funding from NIST, through the NIST-funded Center of Excellence, led by Colorado State University. And our goal was to develop an open source model called INCORE. It's called Interdependent Networked Community Resilience Modeling Environment. The main component of it is a Python package that allows us to apply the hazards to the infrastructure. So basically, do these types of fragility analyses and then propagate that in through direct, indirect losses, look at functional, the impact to society and functional recovery of these systems. So that's kind of the overall goal of INCORE. It's also a visualization package. And then down below, you can see there's a lot of behind the scenes computer science stuff, which I honestly don't know a whole lot about, but how they do the web services, the web tools, and so on. The last thing I am a lot more familiar with, that's all of the Jupyter notebooks that have been developed. There's a really nice website with a whole bunch, if you want to use this test bed and do some of these analyses. We've put the Jupyter notebooks up there. It's also a really active Slack channel if you want to ever use InCore. But that's not, InCore obviously isn't needed for the test bed. The test bed was put up on DesignSafe for whatever modeling idea you have. So, but just a little bit more about InCore. Again, this is how several of these types of models work, but you have the input. So coming from the test bed, we have the inputs on the built environment, building stock, and all these networked infrastructures, social systems, for example, population layers, the real market value of the buildings, things like that. That's all on the input. The hazard model, in our case, was all done externally using some high fidelity inundation modeling. So that's all outside, depending on, if you're doing other types of work like tornadoes and so on, the hazard can be done internally. But these are all like fed into InCore, and then we can do things like, looking at the damage, calculating direct, indirect losses, trying to model the recovery times, optimize, for example, mitigation efforts, and then looking at things like different policy levers, whether you would move critical facilities out of the inundation zone, for example. That can all be done using this model. I'll go through a couple examples just to take a look at some of the things that have been done. And as I mentioned, a lot of this stuff is available through this site at NCSA, where we have the different Jupyter notebooks. But here's an example, one of the first ones that we did, where again, it's just kind of straightforward fragility analysis, where we have the building stock here on the left. We've got the information about the flow depths from the tsunami on the bottom left here. And then we want to analyze the potential for, this 1970s, 1980s-ish hotel to be completely destroyed by the tsunami. So it's, we would go, for example, the InCore selects the right fragility function, in this case for reinforced concrete building, 3 stories or greater, and turns out to be about a 10% probability of complete collapse from the tsunami alone. So, you just can paint this parcel green, redo the analysis again, in this case for a wood frame structure that's right next door. InCore selects the right fragility curve for that. And you end up with a 90%. So the wood frame structure is way less likely to resist the tsunami forces. And it's simple to do all the different parcels in that area. So it's really nice system. It's all set up to, match the parcel IDs and so on. But this is for a 1,000-year event. So the AEP is shown here, and this is probability of being in a collapse damaged state just from the tsunami. So it's kind of an interesting picture. You can see the residential structures to the north and south. In this case, they're red because wood frame doesn't resist the tsunami very well. And then the central core here, where it was mostly concrete, seems to do a pretty good job. And then you also see a very strong spatial gradient. This is also related to the tsunami hazard. So it's greatest at the shoreline and then decreases as we go inland. This was the work of Kyung-Soo Park, Shafiq Alam. They spent a lot of time doing things like modeling earthquake only. So this is just due to the ground shaking. Here you see the opposite effect, where it's the downtown core that's mostly affected. The wood frame structure seemed to do okay. Opposite for the tsunami, and then we have the combined effect. So you can look at combined damages as well as financial losses. And I think one of the interesting things is, because we have all of these annual exceedance probabilities, it's easy to go through and just loop, from 100-year out to 10,000 year. And then in that case, we can see, for example, at AEP of 0.01, the 100-year event, it's high probability or higher probability, but very low consequence. So there's very little damage in this case. And then if you go to 2,500-year event or larger, it's a much lower probability with much higher consequence. And then the true risk is somewhere in the middle. This was work done, sorry about that. This was work done by Dylan Sanderson, now a postdoc at NIST, Kameshwar is assistant professor at LSU, and then Nathaniel, who did a lot of the population modeling. Here, what they're reporting is what's the effect of tsunamis, earthquakes, and then combined tsunamis and earthquakes on the building stock. And they're able to do this across the different mean recurrence intervals. And again, part of what I think makes the Seaside data set unique is that you can actually do the risk-based calculations. So on the y-axis, we're seeing annualized economic losses. And in the case of tsunami losses, it's really around the 1,000-year mean recurrence interval that the tsunami losses are most significant. But the buildings overall seem to be mostly controlled by sorry, it keeps clicking forward. By the earthquake, which has a much lower mean recurrence interval, for example, the 250-year event. They repeated this analysis for the networked infrastructure as well. You can see the other boxes, B, C, and D, are the transportation network, the EPN, and the water network. And I think what's interesting in this one, for example, in B, you can see that the transportation network is really the risk is really controlled by the tsunami. It's the tsunami that takes out the bridges, for example, around the 1,000-year event. And the water network, since these are buried, they're much more like the buildings. They're really susceptible to the earthquake, and it's really around the 250-year event that you get the maximum risk. And I think with the the ability to do thousands and thousands of iterations, you can really start to see what the uncertainties are. For example, the uncertainties around the water network are extremely large compared to the others. A couple more quick examples. I mentioned debris at the outset as one of the important hazards. So some of the work that was done, this was all done outside of INCOR, was trying to use the damage estimates and then some more high fidelity modeling. This was done with again, outside, doing time-dependent fluid solver that does the overland flow. Hyung-Soo is able to move the debris generated from the earthquake and the tsunami inland. And then you can start to see these hotspots, what happens to the debris, and then try to evaluate, for example, the accessibility to hospitals or other critical infrastructure after a major event. Recently, Mirshad Amini, now assistant professor at URI, what he used the testbed for was evaluating structural retrofit for improving tsunami evacuation. So if you remember that daytime population where there was the hotspot down here, that's where all the people are during the day. It's also the corridor that's most affected by the strong ground motion. And what he wanted to show was that by increasing the retrofit, you have fewer amounts of debris that fall onto the road. Therefore, if you can get rid of that debris, you speed up you have less impedance on the rate at which people can evacuate. So this, she was showing over here the reduction coefficient without doing any structural retrofits for the facade. So that's how he used the test bed. And then Sabaranthanam Kameshwar, assistant professor at LSU, he used the test bed to build a Bayesian model for community resilience modeling, defining resilience as the joint probability of achieving community-defined robustness and rapidity targets. And And he was able to do this across multiple infrastructures, the buildings, transportation, water, and electric power network, and then looking at the combined resilience of the system, and then looking at pre and post mitigation efforts. So that was his work. And yeah, that was the last example. And I have here now a list of papers. This is page 1 of 2. That just have, just a whole bunch of people doing different projects with the testbed. Colleague Paolo Cardoni, he's the co-author on many of these with his students. They've used it quite extensively as well. And almost the last slide, I just wanted to thank the team that did a really great job putting the test bed together, especially people I've mentioned, Hyung-Soo, Shafiq, Kameshwar, Mershad, Dylan, Nathaniel, Wei Young. These are all the students, postdocs who were initially involved in the project, as well as my longtime collaborator, Andre Barbosa, Zhang Li, who is the Deputy Associate Director at NCSA and kind of the lead guy behind INCORE, Harvey Cutler, who led the CGE development, and John Vandelant, who has really led the team and encouraged us to put the Seaside Testbed together. Would also like to thank Maria and the whole Design Safe team. They provided a lot of expert advice and feedback on how best to organize this testbed. So I'm not sure that we had the best ideas going in, but certainly working with Maria really straightened out a lot of ways in which people can approach the test bed and ways that we can add to it. So really want to thank the team there. There's a missing spot in the bottom because we do have postdoc opportunities. So with all the students moving on, we do have an opening, not necessarily to work on the Seaside test bed, but definitely to work on more of the INCORE modeling and working with Hurricane Ian as a hindcast. So with that, I want to thank everybody for listening today, and happy to take any questions you guys might have.
All right, thanks, Dan. One of the problems with this webinar format is that you don't get to hear the thunderous round of applause that everyone, as they clap on the other end. Really an interesting talk. Thanks for coming today. So we've received 5 questions in the Q&A. Feel free to type them in there if you have questions, and I'll just go through them in the order that they came through. So first, did your team collaborate with Dogami tsunami scientists on the Seaside project? And I think that's the Oregon Department of Geology and Mineral Industries.
Yep.
Is that right?
Yep. Yeah, we didn't necessarily collaborate directly on it, but we were in communications with them because they developed a lot of really high fidelity scenarios of the tsunami inundation. And so we wanted to see how do our results compare with their inundation maps, and what we were calling our 2,500 year event. How did that compare with what they were doing? So we were really interested in from that perspective. More recently, they've been doing a lot of work using HAZUS to identify what the vulnerabilities are in our area, in a lot of the counties up and down the coast. Haven't quite connected with them on that one, but have definitely read their reports. They're doing a lot of great work.
Great, thank you. Second question, how does the CGE model compare with running HAZUS for loss estimates?
That's a great question. We have not compared directly to HAZUS for the loss and damage yet, but I think that's something that we would really like to do. I think we tried HAZUS MH a couple of years ago when it first came out for tsunamis, and we couldn't get it to work, but that was probably our fault. And then we just felt like we had too many things going on, so we said, okay, let's drop HAZUS. But I think it's time to pick that one back up again. So yeah, it would be very interesting to make the comparisons with HAZUS, as well as the Design Safe, the Sim Center is also making some really nice tools. I think an intermodal comparison using this type of test bed, I think, would be really valuable.
Right, great. And then the previous questions were anonymous, but this one is not. Naveen asks, why does the risk reduce beyond the 100-year return period? Sorry if I read it wrong.
Yeah, the reason why it goes down is because the risk is the probability of that hazard. So, you're dividing by, a larger number each time. And if you could almost say like, well, if there's nothing left to get destroyed, you've destroyed everything, let's say around the 1,000-year event-ish, then you're just dividing by a bigger and bigger number. So the risk is going to go down. So it's the shape that we had for that curve is really common, where you get a peak and then it goes back down again.
All right, thanks. And then a question too, will you disseminate this information in plain language summaries to local agencies, for example, to the Seaside Emergency Manager?
I would be very happy to talk to the Seaside Emergency Manager. I think that one's on me. I was up there years ago, and they were a really great partner. So I think that's up to me to get back up there. But I've given this talk out on the coast in Newport a couple times, and I really enjoy the feedback that we get from coastal stakeholders. So everybody listening as well, I'm sure you guys have had opportunities. I think it's great to be able to go out and talk to general public.
So it's kind of a personal follow-up question to that one from me. When you produce these maps that show a bunch of red buildings, local people might get upset or worried. Have you received any of that kind of feedback from Seaside residents or managers?
No, I think the general sense of like, can we work towards solutions is good. That I think the coastal Oregon communities that I've met are extremely well educated on the hazard over the past 20 years. There's been, especially since 2011, but maybe going back to 2004 with the Indian Ocean tsunami. I think the feedback is overall positive if we're going at it from a point of view of like looking to co-produce solutions. I think just saying there's a big monster out there waiting to happen, they already know that. So I think going at it from what are some of the solution alternatives, I think they're very engaging. For example, with evacuation planning, I've found the communities to be very engaging and to always come up with ideas I never thought of. Like we modeled the road network, as you would for, open maps or something, but they also know there's a vast network of logging roads, and so they're asking, well, what if you map the logging roads? How would that change accessibility and transportation? So usually they've got ideas of their own, things about the accessibility to fuel and other resources. So I've always found it's just really fascinating conversations.
All right, great. So has anyone tried to use this testbed data to apply for earthquake-tsunami mitigation grants?
Not that I'm aware of.
If they do, hopefully they'll cite the DOI to the data set, right? That's a little pitch for data citation practices. Hopefully people are citing that one properly.
And I think that ties into the previous comment too, of like really needing to disseminate this in plain language, and then seeing to what extent they can use this information for mitigation grants. But I think the goal is, let's say, for example, Mershad's work on how retrofits of buildings, we kind of know how, the dollar value for a retrofit building for the earthquake, but his work is kind of interesting because it also implies there could be additional benefits for the evacuation. And so I think trying to put that into plain language and then talking to the local stakeholders might be an important next step for us.
Yeah. And then the last question we have so far is from Justin Bonus, who says, I'm interested in making an open source mid to large multiple debris load simulator on structures for Seaside in Hydro UQ. I can see that there will be transient debris fields, tourist cars in parking lots. What are some constant sources of large debris in Seaside, and where are they? And then I had kind of a question related to this too. Do the fragility functions include the effects of debris on structures, or is it just the water? So maybe I'll just ask both now, kind of as part of
Yeah,
this.
two-part question. The second one, if the fragility function is based on observations, for example, wood frame buildings after the Indonesian tsunami, I would say it contains everything, including debris. If it's a physics-based fragility function where they're just loading it with, using, fluid drag on an element and then the element breaks, then no. So I've seen the fragility functions both types. So you really have to decide which one you're using, whether it incorporates debris or not. I think there's a very interesting research question on how you would incorporate debris, like cascading debris, using this probabilistic approach. There's a lot of work on debris impact on a column and stuff like that, but I think community scale debris is still important research question, both for tsunamis and hurricanes. So yeah, it's something that this type of testbed could be used for. There's the question about transient debris fields like cars, parking lots, that kind of stuff. I think the most constant source of debris, of large debris, are the buildings. There's no port facility, for example. As you can see kind of from the picture in front of us that, it's mostly just buildings. I would say they're the largest sources of debris. But cars, again, for going from day to night or weekend to weekday, I think cars are probably the other big source of debris.
All right. And there is now a follow-up. Have you done any validation on debris estimation and its movement?
Yeah, that's a great question. We did the same researcher who did the debris modeling. He did a debris experiment at our experimental facility. So he's looking at how well the models work against lab data. I think that's kind of the most validation I've seen. We actually ran a tsunami debris modeling workshop for NTHMP. That was led by Pat Lynette, also mentioned him from USC. We used data from the experimental facility here, as well as one data set that was developed in Japan in a laboratory. But the general idea was that the observed field data sets didn't have enough certainty on the input conditions, like what the wave sources were, to be used for benchmarking. So it's still based on lab data at this point. The qualitative description, like, you see the rack line where you get the maximum extent of inundation, that's been observed, for a long time. I think that was the best that Hyung-Soo could do for the Seaside one, is just say it seems to be reproducing qualitatively what one would see during a tsunami.
I did have one more question too about I think I understood correctly that you modeled the earthquake rupture as a Poisson process.
Yep.
Is that right?
Yep.
It has been quite a while now since the last one happened. And is there information to help guide, selection of that rate, since, it is non-Poisson?
Yeah, that's a great question. There's an ongoing project, NSF-sponsored COPE project, where there is a group that's actively looking at how to come up with better probabilistic hazard models for these subduction zone earthquakes and tsunamis.
Mhm.
So I would say what we did was just kind of follow what people had done in the past, whether it's right or wrong, just to get kind of a consistent starting point. So I would be a little bit hesitant to say like this is the true mean recurrence interval for this tsunami for this location. I think as a test piece, we have, and again, this goes back to the really good question about Dogami. I think we, as a test piece, as a test bed, I think we have a reasonably good suite of tsunami hazard data that reasonably represents 100-year, 500-year, and so on. But I think there's definitely room for the experts, the seismologists, and people doing oceanography to really come up with better probabilistic tsunami hazard maps.
Great, thanks. And then
I like
there, there
I
are a
like
few,
the what's that?
there are a few more questions. I don't know how long do you want to continue answering them, or
Yeah, these are great questions. Happy to answer them. And if I don't get to your question, if you can send me an email, I'm happy to answer that as well.
all right. So actually, one is more of a suggestion. You may want to consider presenting this information at the next National Tsunami Hazard Mitigation Program meeting. And then,
I have presented to NTHMP previously. It was over COVID. I remember it was all online, but I would definitely be excited to go to a NTHMP meeting in person.
great. And then Naveen has another question. How do you see that we scale or create more such detailed exposure data sets for other regions at risk? Looks like a lot of work, much needed work. Also, any comments on the collaborative effort behind putting it together, and what were some of the challenges?
Wow, that's a fantastic question. Yeah, I would say, career-wise, this has been one of the most rewarding things I've done. Really trying to build this multi-component data set that has a lot of use for a lot of people. So it definitely was a lot of work, but definitely worth it. Having a place like Design Safe to host it makes it even better because, as a postdoc leaves and they ask me, I'm like, I don't know where the data is. But having it on Design Safe makes it worthwhile. I would say the challenges, I would say, is when is it good enough? Like, okay, it's not perfect, but is it good enough for what people need to use it for? So for example, the building stock, we could still be working on the building stock alone just to make it more identical to what's out in Seaside. But at some point you have to say, okay, if I've got X% wood, X% concrete, I've got a reasonable representation of a small coastal town. So I think that was one of the hardest challenges, was like, when is the data set good enough in these different components? I would say for me, the other big challenge is on the social science side, because I'm not a social scientist. So trying to understand what is needed, what are some of the issues as far as like personal information and things like that. That was a little bit tough. I think one of the other big limitations in modeling this is the city is embedded in a giant disaster. And so, it's not like this little city just got hit. It's like the entire region. So there would have to be ways to look at the interconnectivity between this town and, say Metro Portland and stuff like that. So but that's more on the modeling side of things. Yeah, I would say, the Nihiri Summit that you mentioned, we're going to do that again in 2024. So next May 14 and 15. And one of the one of the themes is, trying to build more of these data sets. And I think one of the big needs is a real data set, a real place like, let's say Fort Myers Beach or something like that, and then track the recovery efforts. So having real data on recovery, I think that's another missing piece on the resilience modeling.
All right, great, thank you. I think I'll go ahead and take over the share if that's okay.
Yep.
All right. I actually can't steal your share. All right, thanks. I think Natalie probably could, but I'm not the host. So I did want to mention that all of our webinars are recorded, and it'll take a little while until it's available, but you will be able to find it on our YouTube channel and through the Design Safe Training Archive. It'll be there. There's many hours of videos at this point for everyone to go watch. Then here's that QR code for the survey. Please take a moment to complete the survey. We really do use that information to make these webinars better, improve them each time. And it's also part of our NSF site visit. We like to show feedback and that we're doing our assessments and making things better, continual improvement. And then I just want to thank Dan. Thanks a lot for being here. It was a great presentation. Really enjoyed it. Thanks also to Ellen and Tim, Charlie, and Dan Stanzione, Tracy, Hedda, and Natalie for helping to put this on. And if you have additional questions, feel free to reach out to us. There's a help menu on Design Safe. You can also find us on Slack and ask us questions there, or email us, or fill out a ticket. We do provide a lot of help with data curation and have office hours for that. And Maria is great, as Dan mentioned. So anyway, feel free to make use of these Design Safe resources. And I want to thank all of you too for being here today. Thanks for joining us.
Thank you.